Hello, I am Giulia Lupi and today I will present a workflow for extracting cell trajectories from videos capturing cellular movement. Specifically, I will demonstrate how this workflow has been applied to data involving macrophages moving during wound healing. The area denoted by a red rectangle is the site of the wound, and the macrophages are moving there to facilitate healing. Upon closer examination of the data, two main issues that could cause problems in segmentation are apparent. First, there is image noise, which, if not removed, may be detected as objects during segmentation. Secondly, the macrophages exhibit different image intensities. Using a global segmentation method may lead to the detection of macrophages with brighter colors, while the darker ones may go undetected. For denoising, there are many possibilities. Here, I will explain one of them, which is called space-time filtering. The image, denoted by the function u, evolves in time according to the following partial differential equation. If we consider only the second part of the equation, without the term CLTU, we obtain the so-called Perona-Malik equation, a well-known equation among computer scientists. It removes noise while preserving the edges of objects. On the other hand, CLTU is a function that maintains temporal coherence. For a pixel in a time frame, the value of CLTU is calculated based on the pixel's brightness in the previous and following frames. For the thresholding technique, we used Otsu's method. This technique determines the threshold value by separating the image into background and object, finding the image intensity value that maximizes the variance between the two classes. Specifically, we use the local Otsu method, which calculates the global Otsu method in a local window. This is done because, as mentioned earlier, the image intensities of the macrophages can vary significantly. A global threshold technique might place macrophages with weaker intensities in the background class. The result is shown in the picture. This slide illustrates the contribution of space-time filtering. On the left, you can see the result of local thresholding with space-time filtering, while on the right, you can see the result without filtering. We can detect more macrophages thanks to the function CLTU, which maintains temporal coherence. Finally, we apply the so-called subjective surface method to eliminate artifacts from local Otsu's method and smooth the insides of the macrophages. The image, again indicated by the function u, evolves in time according to the following partial differential equation. The results are shown on the left. At the top, we have the original images. In the middle, the result of filtering and local thresholding. And at the bottom, the result after subjective surface method. As you can see, all the small noise present in the middle images is removed. Once the shapes have been extracted, the first step in finding the trajectories is to locate the cell centers. We apply the so-called time-relaxed aconal equation, which allows us to find the distance from the cell's boundaries. The approximate cell center is then chosen as the point with the maximum distance. The cell tracking algorithm is organized as follows. First, we compare two time frames and connect two cell centers when the cells overlap. From this step, we obtain partial trajectories. To connect these partial trajectories, we assume that the reason for non-overlapping cells is their relatively fast movement. Consequently, Non-overlapping cells maintain their direction of movement. The connection of partial trajectories is carried out using the tangent approximation. This slide shows the final result of the workflow. As you can see, each macrophage is nicely tracked during its movement towards the wound.